Alright, so our second lesson with waves is all going to be based on the interference of waves. What happens when one wave hits another. Okay, we're going to use something called the principle of superposition. I know that sounds kind of scary, but all it says is that at any point, right, if you have two waves, all you have to do is add the amplitudes at that point. And when you do that, you can have two different types of superposition. One, in this case, if you have the amplitudes here and here, so for example right there and right there, they line up, they're both positive amplitudes, they're going to add and become an even bigger crest. These troughs here and here will line up to become an even bigger trough. Okay, so when we have that, two crests lining up to be a bigger crest and two troughs lining up to be a bigger trough, we call that constructive interference. If we have the opposite, where a crest meets a trough, they line up and they actually, you get a positive amplitude and a negative amplitude. They add to something that is close to zero. So once again, if you have, say, a crest meaning a trough, positive amplitude and a negative amplitude, those will add to close to zero. If they're the same amplitudes, the magnitudes, then it will add to zero. This is called destructive interference. Okay, and I can show you what that looks like. So over here, what I'm going to do is create a pulse. Now this is currently a free end. Okay, so when it reflects off a free end, it's not going to get inverted. So it's going to be a pulse up here, and then a pulse up here, which will bounce back. Watch what happens when they overlap. It's in slow motion, so you can see it happen. Now currently I have this on damping, so let's just remove damping and see what happens. That damping just means it loses energy, and so its amplitude decreases over time. But if we get rid of it, okay, here's where the height normally is, and it goes much higher than where the mouse was. Okay, now let's look at the opposite. I'm going to do a fixed end. So this one's going to come back inverted. So we're going to have a crest meet a trough. And let's see what happens. Again, in slow motion. Notice where my mouse was? Notice that the particles of the wave at that point where they meet pretty much don't move. Okay? So that's destructive interference. And after they interfere destructively, then they just keep moving the same direction they're moving in like nothing ever happened. But when they meet, that is when the amplitudes will add. That's called superposition. Okay, so the next kind of interference I want to talk about is a special kind of interference. It's called a standing wave. Now, when you get one wave coming in one direction, another wave, an identical wave, same frequency, amplitude, wavelength, everything, they will interfere in a very, very special way. You've seen it before. Looks like this. It's called a standing wave because it looks like it's standing still. I mean, you can clearly see right here is an area of destructive interference. At that point, the string never even moves. This alters between a crest and a trough. Both are constructive interferences. Okay? I can show you on here as well. If I have it oscillate. Okay? that will also produce a standing wave. Areas of constructive interference and areas of destructive interference. Oh, it just changed a bit. I got the wrong frequency. But there you go. Areas of destructive interference and constructive interference. Now the areas of constructive interference are called antinodes. Okay, so this is an antinode, this is an antinode, that's an antinode. Now the area of destructive interference are called nodes. Okay, so right here would be a node, there would be a node, here would be a node. Okay, so in our case we have 1, 2, 3 antinodes and 1, 2, and then you can consider the ends a node as well. Okay, if it's a fixed position. If it's not a fixed position, then it would be an antinode because it would be free to vibrate up and down. So that would require a different frequency. We'll talk more about that later. Okay, so this is also a picture of a standing wave, where here you have your nodes, and you'll have a node at a fixed end, and then your antinodes here alternating between crest and trough, and here alternating between crest and trough. Now this leads to one more concept I want to talk about, and that's resonance. Notice in this example here, those antinodes started to get very, very big. That's because this oscillator was oscillating the wave at just the right frequency. So think of it as pushing a child on a swing. You can push fast like this, they're not going to really get higher. You can push slow, and as they come back, you just don't do anything. And then push again, right? They're not going to get higher. You probably noticed at just the right frequency, you'll get higher and higher and higher. So resonance is an effect where if energy is transferred at just the right frequency, it'll increase the amplitude to very, very great amounts. And I can show you a couple examples of that. We'll look down here. So right here, you can see I have 2 tuning forks. And I'm going to set one of them off. Listen very carefully. Even though I held one to stop the vibrations, you could still hear it. Listen again. One more time. Any idea as to why you can still hear it when I stop the vibration? So if I show you that again. So the vibrations that this one causes, and we'll talk about sound waves later, sends vibrations in the air around it at a certain frequency. Each tuning fork is at a different frequency. This tuning fork is identical to this one, which means it wants to vibrate at the same frequency. If it wants to vibrate at the same frequency, all you need to do is hit it with something at that natural frequency, and resonance will occur, and it will start to vibrate, and its amplitude will start to increase. So let's go over this example. This is just testing our knowledge of the principle of superposition. Here we have 2 waves. This one, the square wave, and this one. And they are going to move towards each other at the same speed, and eventually they will meet. And the question says, what will they look like when one is perfectly over top of the other? Okay, well, if they're perfectly over top of each other, then this portion here will be over top of this portion here, and similarly, this one here will be over top of that portion there. Okay, well, let's look at these first two portions then. This one has an amplitude of 2, and when it goes over top of this one, that one you can consider an amplitude of -2. So that is destructive interference, and that is perfect destructive interference. They're going to add to 0, 2 plus -2. Well, what about the next two? This one here will be right over top of this one here. You can think of this having an amplitude of 1 on our grid here, and this one too. So when they go over top of each other, they will have an amplitude of 3. So what will this look like? Well, one is destructive interference, and the other one will go upwards 3 units. So when they are directly over top of each other, it'll look something like that. And then once they pass each other, this will just look like as it is, moving to the left, and this one will look like it is moving to the right. All right, so next example. Here we have a standing wave generated in a string so that 3 loops are present. So let me attempt to draw that. So we have 1 loop, 2 loop, and 3 loops, like that. There we go. The length of the string is 15 meters. So this length is 15 meters. And the frequency of the source is 2.5 hertz. Now that's important because you can only ever change the frequency at the source. So that's not going to change. Find the speed of the waves and the wavelength. So the wavelength, and this is why I drew a diagram, I highly recommend you're always drawing diagrams, would be from, say, here to here. That is 1 full cycle or 1 wavelength. Now the distances between successive nodes are the same. So what we can do is we can figure out the distance between any specific set of nodes because there is 1, 2, 3 distances between our nodes. And they are perfectly split into equal portions, so each portion would be 1/3 of 15, which would be 5 meters. So this is 5 meters, that's 5 meters, and this is 5 meters. Therefore, 1 wavelength, which is 2 nodes, would be 2 times 5, or 10 meters. And once we know the wavelength, we can find the speed using our universal wave equation as 10 meters times 2.5 hertz. Forgot meters here, which would be 25 meters per second.